Hi and welcome to this new video. We will talk about the transient response of the second order circuits. This is our third example. We have a series RLC circuit here with the values shown here for the components, and the independent voltage source is also given as 48 volts. What we'd like to know is the voltage across the capacitor VC for time larger than 0. And we assume in this case that the capacitor and the inductor doesn't store energy, and they are the initial values for them are 0 after the switch, just after the switch is closed. So what we did also for the previous two examples, we will carry out the same procedure here. So what we like to know is the capacitor voltage across the VC, and that will be a summation of the forced response and the natural response. So let's start with the situation number 1. There's actually a situation for time less than 0, actually before the switch closes. So then we have actually the situation as follows. The current doesn't flow actually through the inductor, resistor, or the capacitor, so the IL will be 0 and the VC will be also 0 because there is no connection to any source. So that will bring us to IL at 0 will be 0 amps, and the capacitor at 0, that's always 0 volts. And this is one of the initial values we will use in the analysis we will carry out later on for determining the VC. So this is actually number 1. Okay. The next one is actually the situation for just after the switch is closed. So that means actually at t 0 plus, actually what we need. So what we have is the following. The circuit is now connected to the voltage source Vm, and we have the following circuit. So what we'd like to know is what is the capacitor voltage for this case. So 0 plus, and what is of course the inductor current for this situation. In particular, we are interested in the capacitor voltage, but so we sometimes use and need the inductor current also to carry out the calculations. So for the continuity condition, we know that the capacitor voltage cannot change instantaneously. That means the capacitor voltage at 0 plus is equal to the capacitor voltage at 0. That will mean 0 volts. That will stay the same. It's actually the same for the inductor. So inductor at 0 plus is equal to the inductor at 0, and it will also stay at 0 amps. So this is actually the situation for continuity. Okay, and if I now carry out the analysis using the Kirchhoff current law here, what do I have? I will have the Vm is equal to the inductor current L times R, that is the voltage drop across the resistor, plus the VL plus the capacitor voltage for this. Now if I now evaluate this at 0 plus, so I will remove the t's here, and I will say, okay, this is actually evaluated at 0 plus, 0 plus, 0 plus. What do I get? I will get the following. This is already given, it's 48. Since the inductor current is 0, so the first part here after the equality sign is 0, the inductor voltage, we will keep it here as shown, and this will be also 0. So that will bring us to the inductor voltage at 0 plus will be 48 volts. So we will keep this, we might need it in the future analysis. What we of course require is the initial value for the capacitor and also the derivative of the capacitor evaluated at 0. So what I mean by that is the following. I also need this. So to determine that, I require the following. I can use the Kirchhoff current law, which is actually very simple here. So this is actually the following. The IL at 0 is equal to IC at 0. And there is a formula for the capacitor current, which is C times the derivative of the capacitor voltage. And that's actually the expression we require and we are looking for. So as you can see, the left side of this equation is 0, the right side is the capacitor C capacitance, that's 400 nanofarads, and I can now calculate the expression for the derivative of the capacitor voltage evaluated at 0 or 0 plus, it doesn't matter, that's exactly the same thing. So I will get the following, I will get the IL at 0 plus divided by C. So what is this? Now, I have IL at 0, which is 0, so that will bring actually here the 0 volts per second. And this is actually the second initial condition I will need for set up the final and the total response. Okay, that's actually for this part. Let's move on and let's look at the first response, forced response. That's actually the second step. So forced response, how do I determine forced response? I will close the switch, of course, and I will look at this circuit, and I will again wait such that the steady state is satisfied. So there's a steady state situation, the inductor will be a short circuit and the capacitor will be an open circuit. So I will again redraw that for forced response situation. So forced response. And it's actually also the situation for final value. Okay, what do I have? I will have the voltage source Vm. Okay, let's make it Vm. I have the resistor R. The inductor will be a short modeled, and there is also a capacitor. So this one, capacitor voltage at infinity, this means actually the steady state value of the capacitor will be just the open circuit voltage, because there is no current flowing through the resistor R. So that will be also Vm, and Vm is 48 volts. And since we know that the forced response is equal to the final value of the capacitor, this is just also 48. So I will use this in the final result. I will require this. Okay, so that is actually the following. This is the second step. The third step is actually going to the natural response. Again, for the natural response, I will look at the situation when the switch is closed, but I will disable and I will turn off all independent sources. That means actually we have only one independent voltage source here, that will be a short. I will look at the situation with only R, L and the C. So the situation for the natural response is the second situation. So natural response. So the circuit is as shown. We have the short created by the Vm, and we have the other three components present. Okay, this is actually the situation. I have here the capacitor voltage. The current through the inductor is still running as shown. So what is actually the situation here? Now we can say the following: the current through the inductor is the same as the current through the capacitor. That's true because this is in series. That's one of the conditions. And we can also make a loop, which is the IC times the resistor R, that's actually the voltage drop across the resistor, plus the VL plus the VC, that is the capacitor voltage, will be 0. Okay, so what can I do here? I will use some of the formulas we already know for the inductor voltage. So for the inductor voltage, VL, we know that it's related to the inductor current, derivative of that in this fashion. So L times the time derivative of the inductor current, and we have also the capacitor current, which is the C times the capacitor voltage, time derivative of that. If I use these two formulas in this expression to set up the second order differential equation, I get the following result. So I will have R times C, and the derivative of the capacitor voltage, the first derivative, that's for the first term. The VL will be L times the first derivative of the inductor current, and I will keep the VC because I would like to have a differential equation with only unknown or the variable VC in place and all constant. So I will have to get rid of the IL, but I know that IL is equal to IC, and again I know that IC is equal to this expression. So again I will get another VC expression in the equation, which is actually what I want to do. So if you fill in this, and if you continue the analysis, you will get, it's actually very easy to do, so I will show you the final result. So the final result will be this, the second derivative of the capacitor voltage plus the R divided by L, actually this the situation here, times the first derivative of the capacitor voltage plus 1 over LC times the capacitor voltage. This is actually a very famous expression. You can see this for RLC circuits in series. Most of the time people write this directly without going through the analysis, but I have shown you how you can do this. Okay, now let's fill in the component values that are given. So let's use that. What do we have? We have the R and the L and the C. So if I substitute this, I will get the following. I will get the second derivative of the capacitor voltage divided by the second derivative of the capacitor voltage, plus 2800, that's actually 280 divided by 0.1, that's actually this one, and this is the first derivative of the capacitor voltage, and then 1 over the product of the LC, that will give us 25 million, so 25 times 10 to the power 6 VC, and it will give us 0. I will now use an operator to carry out the analysis here. So actually what I want to do is I will set S, this is Laplace parameter, also called, set S equal to the first derivative of the capacitor voltage, so the S squared will be the second derivative of the capacitor voltage, and the zeroth derivative will be the 1. So actually if I have no derivative, it will transform in 1. So that I get the following transformation. I will get the S squared plus 2800 S plus 25 times 10 to the power 6 is equal to 0. Now, if I want to calculate the roots, I can use the formula for this equation, which is actually very familiar and very standard. So let's do that. So for the two roots, 1 and 2, I have minus 2800 plus or minus the square root of 2800 squared minus 4 times 1 times 25 million divided by 2 times 1, which is actually also 2. So if I calculate this, what do I get? I will get the following, minus 2800, and in the square root I will get 9216 times 10 to the power 3, but it's a minus sign, and I will have divided by 2. Now what you have is the following. Because it is a minus sign, we can get rid of the minus sign by placing a j, so imaginary operator, at the outside of the square root. So I will get the following. So I will have S1 or 2 is equal to minus 1400, so actually I divide by 2, plus or minus j 1/2, and then the square root of exactly the same thing, but then positive. Okay, that's actually for this situation, and if I simplify this, calculate it with a calculator, for example, then you will get the expression which is much more clear than what we had. Okay, this is actually the situation. What you see is you have those two roots or two poles which are complex. We have a real part and imaginary part. So I can already say one of the roots S1 will be minus 1400 plus J 4800, and the other one S2 will be again minus 1400 minus J 4800. So actually what we have is, because we have a solution with a complex notation, so there is the real and imaginary part, this is also called underdamped response. So this is actually the different than the first two examples we discussed. So underdamped response. Now for underdamped response, we have also another general formula. So let's also designate the situation here more clearly. So let's make this what is called here, I will call this sigma d, and I will call this omega d. This means a damped radiant frequency, and that is actually the damping factor. So what we have is the following. For the expression of the natural response of the capacitor, voltage will be as shown. It will be e to the power sigma d t, and then in brackets is then a1 cosine omega d t plus b of a2. Let's write a2, and then sine omega dt, and then bracket closed. So if I now fill in what I have, this is the following. The natural response will be then e to the power minus 1400t, and then a1 times the cosine of 4800t, and then plus a2, and then sine 4800t. That's actually the situation for the natural response. So again, we have the two unknowns, which are the required values for the complete solution. And again, I will calculate and determine this using the initial values substituted in the total solution. So I would like to move on to the total solution, which is the summation of this natural response and the forced response, which is shown here. So that's actually the next step. So I will go and move on to the total response. So let's move on to the total response. So total solution or total response. So what is total response? Vc, which is the required value here, the Vc forced plus the Vc natural response, that is, of course, Vc is equal to, what we had was 48 for the forced response plus e to the power minus 1400t, and again the same expression as we had there, a1 times the cosine of 4800t, etc. Okay, that's actually the situation here. We already know we have to calculate the derivative of this to substitute both of the initial values we have determined. So I will also determine the derivative of the expression of the total response. So what is that now? 48, I will lose this, but there is actually an expression here which is actually a product rule. So I will first differentiate this, and I will keep this, and I can keep this and differentiate the situation in the brackets. So I will have the following: minus 1400 times e to the power minus 1400 or 1400 times a1 cosine 4800t plus a2 sine 4800t. That's actually for the first part. Now I will move to the second, because now I have the e to the power minus 1400t, and now I will have to differentiate the situation here. So what I get is the following: minus 4800 a1 sine 4800t plus 4800 a2, and then cosine 4800t. Okay, that's actually the situation in this case. So what do we do? What is the next part here? So our next part is actually use the initial values to calculate the a1 and a2 using these two expressions. This is a very long expression. I can simplify this, but I know when I fill in that for t equals 0, a lot of terms will disappear, so it is actually not necessary at the moment to simplify this. But what I want to do is, I would like to use these two conditions already mentioned here. So this will be used in the first expression, and this will be used in the second expression. What you see is, this is 0, and this is also 0. So that's actually the situation what we have now. So let's move on. So both of them are 0. This will be 0, and this will be also 0. So I will do this one first. I will do it in black. So what we have is the following: this evaluated at 0 was 0. That means actually the following: if I fill in 0 here, this will disappear. Sign of the 0 is 0. This will be 1, so I get the a1, and this is still in place, so this will be 1, so I will get the following: 48 plus a1, that will be 0, and that will mean a1 is minus 48. Okay, that's actually one of the unknowns we already determined now. Now for the second part, I have to use this formula, so I will move a little bit up. So I will say the derivative of the capacitor voltage evaluated at 0 was also 0. So what is this if I fill in 0 here? And this will disappear. This will disappear. The first one, so what do I get? If I keep it like this, I will see everything. So this was actually the following: minus 1400, because that's actually from this part, times a1. That's actually the first one. And then this is just 1, and then minus 4000, plus 4800 a2. So I will get plus 4800 times a2, because this will disappear, this will disappear, these will be 1, and 1 for time equals 0, and this will also be 0. Okay, so if I evaluate this, and using the a1 is equal to minus 48, I will have calculated a2 is minus 14. You can do the math, it's not really easy, not really difficult. So, and then in the final form, I will have this. Of course, I would like to move and determine this expression. This is actually what I need, so I will give it in green. So this is actually where I'm looking for. I work toward this expression. I would like to know the a1 and the a2, and I have now determined both of them, so I'm actually done. So I can say in blue, I can say the following: Vc is equal to 48 plus e to the power minus 1400t, and a1 is minus 48 cosine 4800 t minus 14 sine 4800 t, and this is again in volts and will be valid for time larger than 0. Of course, you can a little bit simplify this by taking some of the factors outside, or take the minus sign outside, but it's already sufficient to carry out the calculations for next analysis. So this is actually the final result, what is actually required. Again, we did it step by step. First initial values, then the forced response, and then using the final value, of course. Then the natural response by disabling the independent voltage sources, combining the forced response and the natural response to come out to the total solution, which is shown here, and then using the initial values to determine the unknown constants. Actually, that's the whole procedure for the second order systems. This is our third example, and with these 3 examples, we have seen actually 3 different responses. In the first example, we had the critically damped. In the second example, we saw the overdamped, and in this example, we saw the underdamped. So that actually completes this example. I hope this was clear for you. And if you have any questions or comments, please leave it in the comment section. I will try to respond to them as soon as possible. And I'll see you next time, and take care, and good luck.